we continue our discussion on determinants. So let us discuss the relationship between determinant of transpose of a matrix and the determinant of the matrix. We will show that determinant of A and A transpose are equal. Of course, we are always assuming that A is a square matrix. Okay. Then we want to show that determinant of A is same as determinant of A transpose. Now, if we take inverse of A transpose, it is transpose of A inverse. And therefore, if A is invertible, then A transpose is invertible and vice versa. So if A is not invertible, then A transpose is not invertible. And so therefore, both of them have equal determinant and it is equal to 0. So last time we proved this fact about invertibility, that a matrix is invertible if and only if its determinant is non-zero. Okay. So because of this formula which we proved earlier, inverse of A transpose is transpose of A inverse. Both the matrix are either invertible or non-invertible simultaneously. So if it is not invertible, then both the determinants are 0. And so we are done. We have proved that they have equal determinant. So we may assume that the matrix is invertible. Now we have proved a structure theorem for invertible matrices. Yeah. So invertible matrices are exactly product of elementary matrices. So since we are now assuming that A is invertible, A becomes a product of some invertible matrices E1, E2, Ek. Okay. So we assume this structure for invertible matrices, that it's a product of elementary matrices. Now transpose of an elementary matrix is also an elementary matrix. You know the structure of the 3 elementary matrices corresponding to elementary row operations. So if you exchange 2 rows, you get an elementary matrix, and its transpose is again an elementary matrix of the same type. Okay. Then you can check for other 2 row operations that they give rise to those other 2 elementary matrices, and their transposes are elementary matrices of the same type. Okay. So, but it is easy to show that if you take an elementary matrix, then the transpose of an elementary matrix and itself, they have equal determinant, because they are you can check very easily that the determinant of an elementary matrix is same as determinant of its transpose. Okay. Yeah. So we know the result for elementary matrices. Now, invertible matrix is a product of elementary matrices, and therefore we will now prove the result for arbitrary invertible matrices. Okay. Yeah. But we know that determinant of product is product of determinants. So if suppose A was product of 2 elementary matrices, okay, then A transpose equal to F transpose times E transpose. Okay. So determinant of A is determinant of E times determinant of F. Determinant of A transpose is determinant of F transpose times determinant of E transpose. Okay. But the formula is true for elementary matrices. Determinant of E is determinant of E transpose, and determinant of F is determinant of F transpose, and so that implies that determinant of A is determinant of A transpose. Yeah? So using multiplicativity of determinant function and the fact that elementary matrices are they satisfy the formula, all invertible matrices are product of elementary matrices, and therefore the formula is true for them also. And if A is not invertible, then determinant of A is 0 and determinant of A transpose is also 0. So we have proved this. Yeah? We have proved this fact in general. Okay. Uh, so as a consequence of this, we see that determinant of a matrix can be also expanded. It can also be expanded using the kth column. Yeah. So we showed that determinant of a matrix can be expanded using any row. Okay, we proved that it was a determinant function, but determinant of A is A transpose. So therefore, if we expand by rows, that is same as expanding by columns of A transpose. So therefore, we can use the first column of the matrix to write determinant of A, and we will arrive at the same formula. Okay. So now we have proved that determinant function can be computed using any row and any column, right? So that is this corollary, that determinant of A is equal to sum of I equal to 1 up to n, and then we take aik, that is the entry in ith row and kth column, and the row numbers are changing. That means we are fixing the kth column. We are fixing the kth column of the matrix, yeah, and then expanding according to the kth column, A1k, A2k, etc. Yeah, and then we take determinant of aik. Because determinant of A is same as determinant of A transpose, this is exactly the same formula uh, if we do the row expansion by kth row. Okay, so this is another formula for determinant. All right. Now these formulas are, if you look at these formulas, they are not efficient. So to calculate determinant of n by n matrix, I must calculate n determinants, which are determinants of n minus 1 by n minus 1 matrix. And each n by n matrix has determinant which has n factorial terms. So just look at the expression here. Aik times this has n minus 1 factorial terms. Okay, this determinant of Aik has n minus 1 factorial terms, and there are n such terms. So n times n minus 1 factorial. So determinant of A is having a sum of n times n minus 1 factorial terms. That is huge. Okay, so we need a more efficient method to calculate the determinant, and that is again given by the Gauss-Jordan method. The Gauss-Jordan method converts a matrix into an identity matrix if the matrix is invertible. Yeah, because we know that the row canonical form of an invertible matrix is identity matrix, and I showed earlier how to calculate inverse of a matrix by converting the given matrix into row canonical form. And then in the augmented matrix, we put identity matrix by the side of A, apply row operations, and convert A into identity matrix, and then the other matrix, identity matrix, becomes the inverse of the matrix. So this method leads to computation of determinant also. Okay, so let us understand that. Okay, so take a n by n elementary matrix corresponding to the row operation. AI is being added. I mean, C times AJ is being added to AI. Right. So take the jth row, multiply that by a scalar C, and add it to ith row. That corresponds to an elementary matrix. You apply the same operation on identity matrix, I get this elementary matrix E. Okay, then the exchanging two rows. So exchange the ith row and jth row of element identity matrix. That gives me elementary matrix. This I am denoting by F. Okay. Similarly, I multiply AI by a scalar C. The C is not equal to 0. Okay, that is the third kind of elementary row operation, and you do this on identity matrix. So take n by n identity matrix and multiply ith row by C. That is this matrix G. Okay. So how does G look like? Yeah. Take the ith row and multiply by C in identity matrix, and this is my G. Okay. And similarly, you can write the other matrices also. Okay. Now, suppose A is an n by n matrix and U is the row canonical form of A. So the row canonical form of A has two possibilities, right? Either it's identity matrix, and that happens when A is invertible. If A is not invertible, then the last row in the row canonical form must be zero. There must be a zero row. If all the row vectors in the row echelon form are non-zero, yeah, then when we convert that row echelon form into row canonical form, then we get identity matrix. Okay. So the row canonical form of an n by n matrix has two possibilities. Either it is identity matrix or the last row is a zero row. Okay. So let U be the row canonical form of A. Yeah. Now, when we apply the row operations, it is same as applying the multiplying the matrix E in certain by elementary matrices like E, G, E, etc., etc. So on the left, I multiply the given matrix by elementary matrices and then arrive at its row canonical form. Yeah? Suppose A prime is the row canonical form. Yeah. Now, in this row canonical form, I use those matrices E, F, G, but you know that determinant of E is 1, determinant of F is -1 by alternating property of determinant, and determinant of G, okay, G corresponds to the matrix which is obtained from identity matrix by multiplying ith row by C. So that determinant is C. Okay. So determinant of G is C, determinant of F is -1, determinant of E is equal to 1. Okay. So when we do these row operations, the determinant of the given matrix is being multiplied by either 1 or -1 or C at every step. Okay. So we keep track of how many times we exchanged rows. We keep track of how many times we multiply a row by a number C. Okay. And this multiplying a given matrix by E does not change its determinant. Okay. So we keep track of these multipliers. These C's are the multipliers. We are multiplying ith row by C. These C's are the multipliers, and every row exchange multiplies the given determinant by -1. Okay. So suppose I keep track of the multipliers C1, C2, CP. They are the multipliers for the row operations, and AI mapping to CI. And our row exchanges have been used to get U from A. Okay. Then for any alternating multilinear function D, D of U, yeah, A, we applied elementary row operations and got U, but U is equal to A, and then on the left, I multiply by certain elementary matrices. So the determinant of these matrices will be -1 to the power R, where R is the number of row exchanges. And then a certain number of times I multiplied a row by a scalar Ci. So multiply that by C1 up to Cp. Those determinants are C1 up to Cp times determinant of A, and that is equal to determinant of U. So we have this formula. Yeah. Now, U is upper triangular matrix. U is the row canonical form, and the row canonical form is a upper triangular matrix. So its determinant is easily found. Determinant of U is the product of its diagonal entries. Right? But if U is the row canonical form, so row canonical form is either going to have a zero row or it will be identity matrix. So if A is invertible, if A inverse exists, then U is identity matrix, and therefore determinant of A is simply minus 1 to the power R C1 Cp inverse. That is the determinant if it is invertible. Otherwise, if it is not invertible, determinant of A is 0. Okay. So this is the Gauss elimination method. Are there any questions? Are there any questions so far? Okay, so this is the Gauss-Jordan method. Yeah. So this is what I explained. Determinant of Fa is minus determinant of A. F is corresponding to elementary matrix, which is in exchanging two rows. Determinant of Ea is determinant of A. This is E is the elementary matrix corresponding to the row operation, adding to Ai C times Aj. Okay. Determinant of Ga is C times determinant of A. G is the elementary matrix, which is obtained from identity matrix by multiplying ith row by C. So therefore, determinant of dGA is determinant of G times determinant of A, and that is C times determinant of A. And that leads to this formula. Yeah, these are the entries of the diagonal entries of U matrix. Yeah, so if U is in row canonical form, this product will be either 0 or it will be 1. Yeah, so therefore, determinant of A is this, right? But this will be either 0 or minus 1 to the power R times C1 Cp minus 1. Okay. Yeah, so this is most efficient. So let me repeat. So you are given a matrix, and so do not use the formula which is expansion of the determinant using rows or columns, or if you have a general matrix, the best way to compute the determinant, one of the best ways to compute the determinant is to convert the given matrix into row canonical form. Yeah. So the row canonical form is either identity matrix or a matrix which has 0 row at the bottom. If 0 row occurs at the bottom, then the determinant is 0, right, by this formula. If the row canonical form is identity matrix, then the determinant of the given matrix is minus 1 to the power number of row exchanges used to get the row canonical form times the product of the multipliers. That is so, and one can keep track of these things and write a program, computer program, to calculate the determinant. And people have done analysis of number of computations required in this method, and it turns out that the formulas for determinant which use row expansion or column expansion are far more complicated in terms of number of computations than the formula which is obtained by applying the Gauss-Jordan elimination method. Okay. Yeah. Any questions? Okay, so let's continue. Yeah. So I'll give other formula for determinant. So take a
Sir,
n by matrix. This is called the cofactor formula. The cofactor of an entry. Take
sir,
the yes.
so can you repeat the what is the determinant A if row canonical form is identity matrix?
Yeah. So if it is identity matrix, then determinant of the U is the row canonical form of A. Okay. So determinant of U, if A is invertible, then a row canonical form is identity matrix, and therefore du is 1. Is that clear?
Yes, sir.
Yeah. So then dA can be calculated. D is for determinant. So dA will be minus 1 to the power R inverse of the product of the multipliers times the product of the diagonal entries of U. But the product of diagonal entries is either 0 or it is 1, because in the row canonical form of A, the last row is either 0 or the row canonical form is identity matrix.
Okay, sir. Thank you.
So that gives a very neat formula for determinant. But there are other formulas. which are used for they are important for theoretical reasons. So let me go there. But the Gauss-Jordan method is one of the most efficient methods to calculate determinant.